Last class we have completed all our strain energy equations, and today we will be doing some problems related to strain energy. So this is a nutshell. The strain energy due to tensile force will be this one, due to shear force, due to moment, and due to torsion, and the general expression for strain energy. So this is what we have discussed in the last class. Now we'll see how a problem arises in strain energy. Okay, determine the strain energy stored in a cantilever shown. Okay, there is a cantilever and this is having a force P at its end. This distance is L1 and this is L2. So from this diagram it is clear and evident that a bending moment occurs due to this load. Since this is a cantilever, there will be a bending moment, and this bending moment have separate effects on 1 as well as 2. So two sections 1 and 2, load P provides bending moment of the beam. So U is equal to m square dx by 2 EI. This is what the strain energy equation looks like. Okay, so we'll go for the bending moment. So you are drawing a section and P, so bending moment will be Px. So this is basic mechanics of solids problem as we have done in MOS. Okay, now there are two sections. So what will be the strain energy of section 1, because for both section the length is different, right? So this will be Px the whole square, only the limit changes 0 to, from here it's 0 to L1, and from the second section L1 to L2, right? So Px the whole square by 2E I1 into dx. Similarly I1 also changes, right? And here it's L1 to L2, here it becomes I2. Okay, clear? You add these two equations and you will get 0 to L1 as x square dx, L1 to L2 x square dx, and if you solve this, p square by inertia will be different for both terms. You will get a solved equation like this: U is equal to p square by 6e into L1 cube by I1 plus L2 square minus L1 cube by I2. Okay. So similarly, if you need to find out the deflection, the question is not asked, but if the question is asked to find the deflection, you just need to differentiate it with respect to P, d by dp of this term. Okay, then you will get that equation. Okay. We'll now next question, determine the deflection at free end of cantilever when a point load is acting at free end. Okay, where the length of the beam is given as L. Okay, now here also only moment is acting. So U is equal to m square dx by 2 EI. Moment is P into x. You just substitute this equation. You will get U is equal to P square L cube by 6 EI, and the same method we'll do this problem. Okay, delta and U you can find like this. Okay. Now we'll do one more problem in today's session. Determine strain energy stored in following system and find out corresponding deflection. So this is more interesting. You have two sections. This is somewhat an angle section. Its height is h and L is its length. So here if you divide it in two sections like AC and AB, in AB there will be a tensile load, and in AC, due to this load P, this will bend. There will be a bending moment. So two equations we have to use. Okay, so here due to force P, for this section it experiences a tensile force on AB and bending moment is created by P on AC. Okay, so due to tensile load, the strain energy will be P square dx by 2AE. This is the equation for that, and that is from 0 to L. Total distance is L. Okay, then you will get P square L by 2AE. Okay, now for bending, that is in AZ, m square dx by 2EI. Here m square dh by 2EI, because this length is h, where h ranges from 0 to h, limit ranges from 0 to h. Okay, so bending of strain energy of due to bending on AC will be P square h cube by 6EI. Total U will be P square L by 2AE plus P square h cube by 6EI, and deflection will be dou U by dou P. Okay, so this is the total deflection for a member having bending as well as tensile stress. We'll go for one more problem, right? A circular shaft consisting of two portions BC and CD of same material and same length but different cross sections are shown. Determine angle of twist when subjected to twisting couple T at end D. Okay, so here they have given a twisting couple or a twisting effect. That means torsion is the torque of T has been applied at this. Okay, twisting will be happening in two sections, and that will be different. Here we are applying it at D, but for CD and BC a twisting effect will be there. Okay, so general equation for strain energy relating to torsion is T square by 2GG into dx. Okay, so for section CD, if you analyze CD, it is from 0 to L by 2 T square by 2G J1, because polar moment of inertia is different since the diameter is different. So polar moment of inertia of a circular section is pi d raised to 4 by 32. Here diameter is d, so it's pi d raised to 4 by 32 for all circular sections. Okay, so now, so for the second section BC, it's same equation but J2, it becomes here it's J2. Polar moment of inertia changes because diameter changes. Pi into 2 d raised to 4 by 32, which is pi by 2 into d raised to 4. So from here, from J1 and J2 can be related as 16 J1 is equal to J2, because you see J1 is pi d raised to 4 by 32, J2 is pi by 2 into d power raised to 4. So in order to become these two same, you need to into this. Okay, so J1, 16 J1 is equal to J2. Substituting in this equation, okay, instead of these two terms, okay, the total strain will be UCD plus UBC. 16 here J1, here instead of J2 we are applying 16 J1, and you will add this. That's all. Okay, 1 plus 1 by 16, it will come 17 by 16. This will be the strain energy for this section. Okay, also by energy method also you can do this. There is only one torsion, right? 1 by 2 T5, 17 by 16 T square L by 4 GG. 5 will be, okay, energy method, since there is only one torsion, you can apply this equation, so that we can find out its phi value. Okay, that's all for today. If you have any doubt, please contact me. Thank you.